Hello and welcome. Find a comfortable place to rest. Let the world outside fade away. Tonight, we're not here for speed or for spectacle. We are here for a slow, deep dive into a new cosmic mystery. This is Plunge into Science, an experience created to both enlighten your mind and calm your spirit. Think of me as your guide, a teacher in the quietest, grandest classroom imaginable, the universe itself. We are going to journey billions of light years away to witness a moment of cosmic creation, a discovery so new it is reshaping our understanding of the universe's most powerful objects. But before we embark on this great journey, let's first ground ourselves. Take a moment and think, what is your favorite planet? Is it the steadfast, familiar presence of Earth, our own blue marble? The mysterious, stormy visage of Neptune, the deep blue giant at the edge of our solar system? Or perhaps the rugged, cratered face of Mercury, forever locked in a fiery dance with the sun? Each one is a world, a place with a history. Hold that thought. Today, we journey beyond planets, beyond even our own galaxy, to a place where two entire galaxies are colliding to form a shape we all recognize, the symbol for infinity. And at the heart of this impossible object, we may have just found something we have never seen before, the birth of a supermassive black hole. To truly appreciate the significance of a single galaxy, we must first understand the grand tapestry into which it is woven. For most of human history, the sky was a two-dimensional dome of fixed stars and wandering planets. The faint, milky band we call the Milky Way was thought to be a cloud or a river of the gods. It was not until the invention of the telescope that Galileo Galilei resolved this band into countless individual stars, revealing that we lived inside a vast, flattened disk of stars. Yet, even then, we believed this was the entire universe. Other faint, fuzzy patches of light in the sky, called spiral nebulae, were thought to be clouds of gas or nascent solar systems forming within our own galaxy. The scale of the cosmos was, in our minds, still relatively contained. This all changed in the 1920s with the work of astronomers like Henrietta Swan Leavitt and Edwin Hubble. Leavitt discovered a crucial relationship in a type of star called a Cepheid variable, allowing astronomers to measure vast cosmic distances for the first time. Using this new cosmic yardstick, Hubble pointed the mighty Hooker telescope at the Andromeda Nebula and found Cepheid variable stars within it. His calculations revealed that Andromeda was not a cloud inside our galaxy. It was another galaxy entirely, a separate island universe located millions of light years away. In that moment, the known universe expanded by an unimaginable factor. Our galaxy was not the universe. It was just one of countless others. Today, we know that the observable universe contains an estimated 2 trillion galaxies. They're the fundamental building blocks of cosmic structure. They come in a beautiful variety of shapes and sizes. There are majestic spiral galaxies like our own Milky Way and Andromeda, with elegant, sweeping arms of young, blue stars and glowing pink nebulae. There are massive elliptical galaxies, giant, reddish spheres of older stars that look like cosmic footballs. And there are irregular galaxies, smaller, chaotic collections of stars with no discernible shape, often born from violent interactions. These galaxies are not scattered randomly through space. They are organized by gravity into a magnificent structure known as the cosmic web. They are strung along vast filaments of dark matter, separated by immense, empty voids. Where these filaments intersect, galaxies congregate into clusters, cosmic cities containing thousands of galaxies, all bound together by gravity. It is within this vast, interconnected web that the story of the universe unfolds. It is a story of birth, growth, and collision. And it is in one of these collisions, in a distant corner of this web, that our story tonight begins. As we gaze out at this web, a structure so vast that it transcends our ability to truly comprehend it, we must ask, is the universe fundamentally a place of isolated islands? Or is it a place of profound, underlying connection? Galaxies may be separated by millions of light years, but in the grand scheme of the universe, they are not isolated. Gravity, the great organizer of the cosmos, is relentless. Over billions of years, it draws galaxies together. And when they meet, they don't simply pass by. They engage in a slow, powerful, and transformative dance that can last for hundreds of millions of years, a galactic merger. This process is one of the primary ways that galaxies grow and evolve over time. Our own Milky Way is a product of countless mergers with smaller dwarf galaxies over its long history, and it is on a collision course with our nearest large neighbor, the Andromeda Galaxy, with a predicted impact in about 4.5 billion years. Now, what actually happens when two galaxies, each containing hundreds of billions of stars, collide? The image that comes to mind is one of cosmic carnage, of stars smashing into each other in a fiery cataclysm. But the reality is far more subtle and beautiful. The distances between individual stars are so immense that when two galaxies merge, the stars themselves almost never collide. A star in a galaxy is like a single grain of sand on a football field. If you were to throw 2 football fields worth of sand at each other, the odds of any 2 specific grains hitting are virtually zero. Instead of colliding, the stars of the 2 galaxies fly past each other, their paths bent and distorted by the immense, combined gravitational field of the merger. This gravitational tug-of-war is what creates the spectacular shapes we see in merging galaxies. Great, sweeping arcs of stars and gas, called tidal tails, are flung out into intergalactic space, creating ephemeral, ghostly structures that trace the history of the interaction. While the stars pass through like ghosts, the gas does not. Unlike stars, the vast clouds of interstellar gas and dust within each galaxy are not small points. They are expansive, diffuse clouds. When these clouds from the 2 different galaxies meet, they slam into each other at hundreds of kilometers per second. This collision creates massive shock waves that compress the gas, triggering a furious burst of new star formation. This is called a starburst. In a merging galaxy, the rate of star birth can be hundreds or even thousands of times greater than in a quiet, isolated galaxy like our own. These starbursts light up the merging system, creating a brilliant temporary beacon that is one of the hallmarks of a galactic collision. It is a process of creative destruction. The elegant spiral structures of the original galaxies are destroyed, but from that chaos, a new, larger, and often more stable elliptical galaxy is born, filled with a fresh generation of stars. This dance of gravity, gas, and stars is a fundamental cosmic process. But what if this process could create something else? Something far stranger and more powerful than just new stars. This is the question that lies at the heart of the infinity galaxy. At the heart of nearly every massive galaxy we have ever observed, including our own Milky Way, there lies a monster, a supermassive black hole. These are not the ordinary stellar mass black holes that are formed from the collapse of a single massive star. Those might be a few dozen times the mass of our sun's supermassive black holes are beasts on a completely different scale, ranging from millions to billions of times the mass of the sun, all compressed into a region of space smaller than our solar system. Our own galaxy's central black hole, named Sagittarius A star, is about 4 million solar masses. The true heavyweight champion in our local universe is the black hole at the center of the galaxy M87, which weighs in at a staggering 6.5 billion solar masses. This is the black hole that was famously imaged by the Event Horizon Telescope, giving humanity its first direct look at a black hole shadow. For decades, astronomers have been trying to solve the enigma of these cosmic monsters. Where do they come from, and how do they get so big? The leading theory has been that they started from seeds. One idea is that the very first generation of stars in the universe, known as population 3 stars, were incredibly massive, perhaps hundreds of times the mass of our sun. When these giants died, they would have collapsed to form the first stellar mass black holes. These seed black holes, residing in the centers of the first proto-galaxies, would then have grown over cosmic time. They would grow by feeding on the gas and dust that falls into the galactic center, a process called accretion. They would also grow dramatically during galaxy mergers. When two galaxies collide, their central supermassive black holes will eventually sink to the center of the newly formed galaxy, orbit each other, and finally merge in a cataclysmic event that sends powerful ripples, called gravitational waves, across the fabric of spacetime. This model of seeding and growing seems plausible, but it has a major problem. We observe extremely massive black holes, billions of solar masses, existing very early in the universe's history, less than 1 billion years after the Big Bang. These are seen as quasars, which are incredibly luminous galactic cores where the central black hole is feeding so voraciously that its accretion disk outshines the entire host galaxy. The problem is time. It is incredibly difficult for a black hole starting from a stellar mass seed to grow to 1 billion solar masses in such a short amount of time. There simply hasn't been enough time for it to accrete that much matter, even at the maximum possible rate. This suggests that either the seeds were much more massive than we thought, or there is another, much faster way to form a supermassive black hole. This is one of the biggest unsolved mysteries in astrophysics. It's a classic chicken and egg problem. Which came first, the massive galaxy or the massive black hole? Do galaxies build black holes, or do black holes build galaxies? The discovery of the infinity galaxy may have just given us our first clue to a radical new answer. To uncover a secret as profound as the birth of a supermassive black hole, a single perspective is not enough. The universe reveals itself in different ways depending on how you look at it. Our eyes can only see a tiny sliver of the full spectrum of light, the range we call visible light. But the cosmos is awash in other forms of light, from low-energy radio waves to high-energy X-rays and gamma rays. To get a complete picture of any cosmic object, astronomers must become multi-wavelength detectives, assembling clues from different parts of the electromagnetic spectrum. The discovery of the infinity galaxy is a perfect testament to this collaborative, multifaceted approach, relying on a team of the world's most powerful observatories. The story begins with the James Webb Space Telescope, or JWST. As a large, cold telescope in space, JWST is the undisputed master of the infrared universe. Infrared light is crucial for 2 reasons. First, because the universe is expanding, light from very distant objects is redshifted out of the visible spectrum and into the infrared. To see the early universe, you must see in infrared. Second, infrared light can penetrate through the thick clouds of cosmic dust that obscure the most active and interesting regions of space, like the hearts of merging galaxies where stars and black holes are born. It was in a deep infrared survey from JWST that the infinity galaxy's strange shape was first spotted. Once the strange object was identified, astronomers turned to other great observatories for follow-up. They used the W.M. Keck Observatory in Hawaii, one of the largest and most advanced optical and near-infrared telescopes on Earth. Keck is equipped with powerful spectrographs, instruments that split light into its component colors, like a prism. By analyzing the spectrum of the gas in the infinity galaxy, astronomers could measure its motion, its temperature, and its chemical composition, providing crucial clues about the dynamics of the merger. To search for the high-energy signature of a feeding black hole, they looked at archival data from the Chandra X-ray Observatory. When material falls into a black hole, it forms a superheated accretion disk that glows fiercely in X-rays. A detection with Chandra would be a key piece of evidence. Finally, to look for powerful jets of material being launched by the black hole, they used data from the National Radio Astronomy Observatory's Very Large Array, VLA, in New Mexico. These jets, if present, would glow brightly in radio waves. Each of these instruments provided a different, essential piece of the puzzle. JWST saw the shape, Keck measured the motion, Chandra saw the heat, and the VLA listened for the jets. It is only by combining these different views that the true, revolutionary nature of this object could be understood. It reminds us that truth is often complex. Does a single perspective ever give us the full story, or must we always seek to combine different viewpoints to get closer to reality? Every great discovery begins with a single moment of observation, a moment when someone sees something that no one has ever seen before. For the Infinity Galaxy, that moment occurred within the digital archives of one of JWST's most ambitious projects, the Cosmos Web Survey. Cosmos Web is a treasury program designed to map a large patch of the sky, about the size of 3 full moons, with unprecedented depth and resolution in the infrared. Its goal is to create a deep, wide census of the early universe, charting the formation of the very first galaxies during a period known as the Cosmic Dawn. The survey produces a torrent of data, images containing hundreds of thousands of galaxies, each one a snapshot from a different epoch of cosmic history. It was within this vast data set that Yale astronomer Peter van Dokkum and his colleague Gabriel Brammer of the University of Copenhagen were hunting for unusual objects. They were not necessarily looking for a newborn black hole. They were simply exploring this new, uncharted territory that JWST had opened up, looking for anything that defied our expectations. And then they saw it. Among the countless spiral and elliptical galaxies, there was an object with a structure so strange and so perfectly symmetrical that it immediately stood out. It looked for all the world like a figure 8 or the mathematical symbol for infinity. The object was given the official designation J1000 plus 0130, but the team nicknamed it the Infinity Galaxy for its remarkable shape. Van Dokkum and his team knew immediately that they were looking at a galactic merger. The 2 lobes of the infinity symbol were clearly the cores of 2 galaxies that had recently collided and passed through each other. The elegant, looping shape was a product of the gravitational forces of their interaction, a snapshot of their cosmic dance. But there was more to it than just a pretty shape. Everything about this galaxy, as Van Dokkum would later say, was unusual. It was incredibly dusty and was undergoing a furious burst of star formation, consistent with a merger. But it was the follow-up observations that would turn this curious object into a potentially revolutionary one. The initial discovery in the JWST images was the first breadcrumb on a trail that would lead them to a conclusion so extraordinary that it would challenge decades of thinking about the formation of the universe's largest objects. This is how science often works. It is not always a single eureka moment, but a slow, careful process of noticing an anomaly, asking questions, and then gathering more evidence, piece by piece, until a new picture of reality begins to emerge. How many other profound discoveries are lying dormant right now, hidden in plain sight within our vast archives of data, just waiting for a curious mind to notice a single, strange detail? Let's now take a closer look at the object itself. What are we actually seeing when we look at the Infinity Galaxy? This is not just a chance alignment of 2 separate objects. It is a single, interacting system, a snapshot of a physical process that is unfolding over millions of years. The 2 brightest regions, which form the centers of the 2 lobes of the figure 8, are the original cores of the 2 colliding galaxies. These are the regions where the density of stars and gas was highest in the parent galaxies. They are like 2 ships passing in the night, their gravitational wakes creating the spectacular structure around them. The shape itself is a beautiful illustration of gravitational physics. As the 2 galaxies approached and passed through each other, their mutual gravity acted like a giant slingshot. It pulled on the stars and gas, accelerating some and decelerating others. This process flung out 2 massive tidal tails of material, one from each galaxy. Due to the geometry of this particular collision, these tidal tails were not just flung out into straight lines. They were pulled into vast, looping arcs that curve back around, crossing over in the middle to create the iconic infinity shape. The crossover point, the very center of the symbol, is a region of immense activity. Here, gas and dust that has been stripped from both galaxies is colliding and piling up, creating a dense, turbulent bridge of material that connects the 2 cores. The Keck Observatory spectrograph was crucial in confirming this picture. By measuring the Doppler shift of the light from different parts of the galaxy, astronomers could create a velocity map. This map showed that the gas in one lobe was moving towards us, while the gas in the other lobe was moving away from us, exactly as you would expect from two galaxies that have just passed through each other. The velocity map also revealed the incredible turmoil in the central bridge region, with gas moving at high speeds and in chaotic directions, a clear sign of the violent collisions happening within the gas clouds. The entire system is enshrouded in a thick veil of dust, produced by the starburst and the death of massive stars. This is why JWST was so essential. Invisible light. Most of this structure would be completely hidden. Only in the infrared can we peer through the dust and see the intricate anatomy of this cosmic collision. This single object serves as a perfect, almost textbook example of tidal interactions in a galactic merger. But it is what lies hidden within the central, chaotic bridge that makes this textbook example unique in the history of astronomy. It forces us to ask a question about form and function. Is the beautiful, symmetrical shape of this galaxy merely an aesthetic coincidence of gravity? Or does the specific geometry of this collision play a functional role in creating the extraordinary object at its heart? As the team gathered more data on their strange new object, they encountered the biggest surprise of all, a discovery so counterintuitive it forced them to question the very foundations of how supermassive black holes are supposed to behave. As we discussed, nearly every massive galaxy has a supermassive black hole at its center. Therefore, in a merger of two massive galaxies, we would expect to find two supermassive black holes, one in the core of each of the original galaxies. As the merger progresses, these two black holes would eventually sink to the center of the newly formed galaxy and merge. This is the standard picture. So, the team naturally expected to find an active, feeding black hole, a quasar, at the center of at least one of the two lobes of the infinity galaxy. They pointed the Chandra X-ray Observatory and the Very Large Array at the system to hunt for this signature. And they found it. They detected the telltale signs of a powerful, accreting supermassive black hole. There was a bright source of X-rays, indicating a superheated accretion disk, and evidence of radio emission, suggesting the presence of jets. The monster was there, but it was in the wrong place. The supermassive black hole was not located inside either of the two galactic nuclei. Instead, it was situated right in the middle in that dense, chaotic bridge of gas and dust that connects the two cores. This was a profound shock. As Peter Van Dockum put it, we asked ourselves, how can we make sense of this? There is no known mechanism in standard galaxy formation models that would place a pre-existing supermassive black hole in this location. A black hole is the most massive object in its host galaxy. It should sit at the very bottom of the galaxy's gravitational well, which is in the core. To move it out of the core and into a bridge of gas between two galaxies would require an almost impossible set of circumstances. Perhaps it was a smaller black hole that was wandering between the galaxies? This was unlikely, as the object was incredibly massive and luminous, clearly a supermassive black hole. Could have been ejected from one of the cores? This is a theoretical possibility, known as a recoiling black hole, where the merger of two smaller black holes can produce a gravitational wave kick that sends the new, larger black hole flying. However, the odds of it being kicked directly into this specific location and the conditions in the bridge made this explanation seem highly improbable. The team was faced with a mystery. They had found a monster, but it was a monster without a home. It was an orphan existing in a place where it had no right to be. This puzzle, this black hole that shouldn't be there, was the key that unlocked a radical new hypothesis. It suggests that perhaps the black hole wasn't pre-existing at all. Perhaps they were not witnessing a black hole that had moved. Perhaps they were witnessing the exact moment and location of a black hole's birth. Faced with a supermassive black hole in a place where no supermassive black hole should be, Van Dockum and his team were forced to think outside the box. If the black hole wasn't from either of the parent galaxies, then it must have formed right there in that dense bridge of colliding gas. This led them to a bold and exciting new theory, a process known as a direct collapse. In this scenario, the supermassive black hole did not start as a star. It did not grow over billions of years. Instead, it was born in a single, catastrophic event. Here is how the theory works. The infinity galaxy merger is a perfect storm of conditions. The collision is funneling enormous amounts of gas from both galaxies into that central crossover region. This gas is extremely dense and turbulent. Under normal circumstances, such a dense cloud of gas would cool, fragment, and collapse to form billions of new stars in a massive starburst. However, direct collapse models propose that if the conditions are just right, if the gas is dense enough and hot enough, and if it is prevented from cooling and fragmenting effectively, then the entire massive cloud can become gravitationally unstable all at once. Instead of breaking up into stars, the entire cloud, containing the mass of millions of suns, could collapse directly and catastrophically under its own gravity, straight into a single, massive black hole. This would form a supermassive black hole seed that is already millions of solar masses from the moment of its birth. It would completely bypass the slow, inefficient process of starting with a single star and growing over cosmic time. This is what Van Dacke meant when he called the discovery as close to a smoking gun as we're likely ever going to get. The evidence all points to this conclusion. The location of the black hole is the first clue. It is exactly where the gas from the two galaxies is colliding most violently. The conditions are the second clue. The region is incredibly gas-rich and turbulent, perfect for such a collapse. The black hole's own properties are the third clue. It is nestled within an incredibly dense cocoon of gas and dust, exactly as you would expect for an object that has just formed from the very material that now surrounds it. The infinity galaxy may be the first time we have ever directly witnessed this process of direct collapse in action. It is a potential solution to the long-standing problem of how supermassive black holes got so big, so fast in the early universe. It tells us that galaxy mergers are not just places where black holes grow. They may be the very forges where they are born, fully formed. This idea fundamentally changes our perspective. We thought of black holes as ancient relics that grew with their galaxies. What if some of them are newborns, created fresh from the raw material of cosmic collisions? Let us now connect this extraordinary discovery back to one of the most persistent puzzles in cosmology, the existence of early quasars. As we travel back in time, by looking at more distant objects, we find that the universe was a very different place. It was smaller, denser, and galaxies were much closer together. Galactic mergers, like the one creating the infinity galaxy, were far more common. It was in this chaotic early environment that we see the first quasars. These are the brightest objects in the universe, shining with the light of 1 trillion suns, all from a region no larger than our solar system. We now know that this incredible luminosity is powered by a supermassive black hole billions of times the mass of our sun, feeding on gas at a furious rate. The puzzle is their age. We have found quasars that were shining brightly when the universe was only about 700 million years old. This is an incredibly short amount of time in cosmic terms. The standard model of black hole growth, where a seed from first-generation stars slowly accretes matter, simply cannot explain it. It's like finding a fully grown giant redwood tree that is only a few weeks old. It defies the known growth rates. To grow a black hole to 1 billion solar masses in 700 million years, you would need to start with a very large seed, and it would need to feed continuously at the maximum possible rate, known as the Eddington limit, for its entire life without ever stopping. This is a highly unlikely scenario. Astronomers have been searching for a way to create much larger initial seeds that are tens or hundreds of thousands of solar masses, to give them a head start. The direct collapse model, for which the infinity galaxy is now our prime evidence, provides a perfect solution. If a merger of two gas-rich proto-galaxies in the early universe can trigger the direct collapse of a massive gas cloud into a black hole of, say, a million solar masses, then the problem is solved. Starting with a million solar mass seed instead of 100 solar mass seed makes it far, far easier to grow to a billion solar masses in the available time. The frequent mergers in the early universe would provide the ideal conditions for this process to occur regularly. The infinity galaxy, while it is not from the very early universe, is a local analog, a present-day example of a physical process that was likely fundamental to shaping the cosmos in its infancy. It is a window into the past. By studying it, we can understand the physics of a mechanism that may have created the seeds for the first cosmic giants, the black holes that powered the first quasars and lit up the dawn of the universe. It suggests that the birth of the first monsters was not a slow, gradual process, but a series of rapid, violent, and spectacular events, born from the collisions of the first galaxies. Does this change our view of cosmic history, from one of slow evolution to one punctuated by sudden, revolutionary creative acts? The discovery of the infinity galaxy does more than just solve a puzzle about the early universe. It forces us to reconsider the fundamental relationship between a galaxy and its central black hole. For years, astronomers have known about a surprisingly tight correlation, called the M-sigma relation. It shows that the mass of a galaxy's central supermassive black hole is almost perfectly proportional to the mass of the stars in the galaxy's central bulge. A bigger bulge means a bigger black hole. This tight relationship suggests that the galaxy and its black hole are not independent entities. They must somehow grow together, influencing each other in a process called coevolution. This brings us back to our chicken and egg problem. Which comes first? Does the galaxy's bulge grow, and the black hole somehow knows to grow in proportion? Or does the black hole grow, and its growth then dictates the size of the galaxy's bulge? The standard model has been that they grow together, with galaxy mergers bringing in both new stars for the bulge and more gas to feed the black hole. But the infinity galaxy presents a fascinating new twist on this story. In this case, it appears that the supermassive black hole is forming first, before the two galaxies have even fully merged and settled down to form a new, cohesive bulge. The black hole is born out of the raw material of the merger itself. This new black hole will not be a passive observer. As it begins to feed voraciously on the dense gas surrounding it, it will unleash a tremendous amount of energy back into its environment. This energy, in the form of radiation from the accretion disk and powerful jets, is called feedback. This feedback can heat up the surrounding gas, blowing it out of the galactic center and potentially shutting off further star formation. In this way, the newborn black hole can directly regulate the growth of its new host galaxy. It could be that the black hole forms first in a merger, grows to a certain size, and then its feedback effectively determines the final mass of the stellar bulge that will form around it. This would elegantly explain the M-sigma relation. The black hole isn't just a passenger in the galaxy. It's the pilot setting the course for the galaxy's future evolution. This turns the traditional view on its head. Instead of a galaxy slowly building its black hole, we have a catastrophic event, a merger that rapidly builds a black hole, which then orchestrates the final construction of the new galaxy. The infinity galaxy could be our first glimpse of the egg forming before the chicken. It represents a shift in our understanding from a slow, coevolutionary process to a more event-driven one, where the major transformative moments in a galaxy's life are dictated by the rapid birth and powerful feedback of its central monster. It forces us to ask if a system is defined by the slow accumulation of its parts, or by the singular, transformative events that punctuate its history. Let us take another moment to step back from the astrophysics and consider the name and the shape of this incredible object, infinity. It is a concept that has fascinated and haunted philosophers, mathematicians, and theologians for millennia. It represents the boundless, the eternal, the unending. And here, written in the language of stars and gravity across a canvas hundreds of thousands of light years wide, the universe has presented us with this very symbol. Is this merely a coincidence of orbital mechanics? Or is there a deeper resonance we can find in this cosmic emblem? The symbol itself, the lemniscate, represents a loop with no beginning and no end. It is a symbol of cycles, and in a way, the process we are witnessing in the infinity galaxy is a profound cosmic cycle. Two separate, ordered systems, two spiral galaxies, are coming together in an act of chaotic destruction. Their elegant structures are being torn apart, their stars scattered, their gas compressed and shocked. It is a moment of unmaking. But from this very chaos, a new order is being born. A new, more massive galaxy will eventually form, and at its heart, a new supermassive black hole, a new center of gravitational power, has been created. It is creation born from destruction. It is a cycle of galactic reincarnation. The infinity symbol here is not just a shape, it is a story. This discovery also touches on our human relationship with the concept of infinity. We live finite lives on a finite planet, in a universe that we now know had a beginning in the Big Bang and will have an end, likely in a cold, dark heat death. Yet, we are creatures who can conceive of the infinite. We can reason with it mathematically. We can be awed by it spiritually. To see this symbol so deeply tied to our own abstract thought manifest on a galactic scale is a powerful and humbling experience. It feels like the universe is speaking a language we can understand. It reminds us that the fundamental laws of physics, gravity, motion, conservation of energy, are the same everywhere, from the arc of a thrown ball to the looping tidal tails of colliding galaxies. The patterns repeat. The dance is the same, just on an infinitely grander stage. What does it mean that our minds can grasp a concept like infinity, a concept so much larger than our own existence? Does it suggest that we are not just observers of the universe, but that our consciousness is, in some small way, a reflection of its fundamental nature? The discovery of one smoking gun is a revolution, but in science, a single data point is always a curiosity. The next crucial question is the infinity galaxy a complete one-of-a-kind cosmic fluke, or is it the first example of a previously unseen, but common, stage in the life of galaxies? Now that astronomers know what to look for, the hunt is on for more of these objects. The very conditions that make the direct collapse possible also make the object difficult to see. The newborn black hole is shrouded in the incredibly dense cocoon of gas and dust from which it formed. This means it is invisible in optical light and can only be detected in the infrared, X-ray, and radio wavelengths. Before the launch of the James Webb Space Telescope, we simply did not have the sensitivity in the infrared to peer deep enough into these dusty shrouds to see what was happening at their hearts. JWST has changed the game. Astronomers are now meticulously combing through the data from Cosmos Webb and other deep surveys, looking for other merging galaxies that share the characteristics of the infinity galaxy. A strange, tidally disrupted shape, a powerful starburst, and most importantly, a luminous quasar that is offset from the galactic nuclei. The initial discovery has provided a clear search template. If this direct collapse mechanism is indeed a primary way to form supermassive black hole seeds, especially in the early universe where gas-rich mergers were common, then we should expect to find many more examples. Finding more of these objects would allow us to study the process in a statistical way. We could see if it only happens in mergers of galaxies of a certain size, or if it requires a specific geometry of collision. We could measure the masses of the newborn black holes to see if there is a typical birth mass. We could study the surrounding gas to better understand the physics of the collapse and the strength of the subsequent feedback. The infinity galaxy may have been the first, but it has opened a new frontier. It is like the first discovery of an exoplanet, which went from a single, unbelievable detection to a field that has now cataloged over 5,000 worlds. We may be at the very beginning of a similar revolution in the field of black hole formation. This raises a fascinating possibility. We look out at the universe and see thousands of quasars, the brilliant beacons of feeding supermassive black holes. We have always assumed these were ancient objects that have been growing for a long time. But what if a significant fraction of them are actually newborns? What if we have been misinterpreting the evidence all along, seeing ancient kings where we should have been seeing screaming newborn infants? It is a paradigm shift that forces us to re-examine our assumptions about the cosmic timescale and the life cycle of the universe's most powerful engines. It makes one wonder, what other fundamental processes of the universe are happening all around us, hidden in plain sight, just waiting for the right tool and the right perspective to be revealed? The story of galactic mergers and the potential for dramatic creation is not just something that happens in distant, exotic galaxies. It is a core part of our own cosmic story, both in our past and in our future. The Milky Way, with its beautiful, serene spiral arms, appears to be an island of stability, but its calmness is an illusion born of a long and violent history. By studying the motions and chemistry of stars in our galaxy, particularly with the incredible data from the Gaia Space Observatory, we have uncovered the fossil record of our galaxy's cannibalistic past. About 10 billion years ago, a relatively large dwarf galaxy, now nicknamed the Gaia-Sausage Enceladus Galaxy, collided with and was absorbed by the young Milky Way. This was a formative event in our galaxy's history. It is believed to have puffed up the Milky Way's disk, formed its inner halo of stars, and triggered a major burst of star formation. This is just one of many such mergers. Our galaxy is still in the process of consuming smaller satellite galaxies, like the Sagittarius Dwarf Galaxy, whose stars are being stripped away to form great streams that wrap around the Milky Way. Our home is a product of collisions, and our future is defined by one. The Andromeda Galaxy, our largest galactic neighbor, is currently hurtling towards us at a speed of about 110 kilometers per second. In about 4.5 billion years, the two galaxies will begin their first close pass. The sky, for any beings who might be on Earth at that time, will be transformed. Andromeda will fill the night sky, a spectacular, swirling tapestry of stars. Over the next few 100 million years, the two galaxies will dance around each other, their structures being torn apart by tidal forces, until they eventually merge into a single, giant elliptical galaxy, which some have nicknamed Milkomeda. This future merger will be a spectacular event. The combined gas from the two galaxies will trigger a massive starburst, lighting up the new galaxy. The two central supermassive black holes, our own Sagittarius A star and Andromeda's 100-million solar mass black hole, will eventually merge, creating a new, larger monster at the heart of Milkomeda. But now, with the discovery of the Infinity Galaxy, we can ask a new question. During the chaotic collision of gas clouds in the Milkomeda merger, could the conditions be right for a new supermassive black hole to form via direct collapse, in addition to the two that are already there? Could our own galactic collision, billions of years from now, become a laboratory for the very process we are now witnessing from afar? It connects our own distant future to this new discovery, reminding us that the cosmic processes that seem so alien are the very same ones that have shaped our past and will determine our ultimate destiny. To truly grasp what a supermassive black hole is and why its birth is such a monumental event, we must move beyond the astronomical picture and delve into the deep physics that governs it. The story of black holes is the story of Albert Einstein's theory of general relativity. In 1915, Einstein revolutionized our understanding of gravity. He proposed that gravity is not a force that pulls objects towards each other, but rather a consequence of the way mass and energy curve the very fabric of the universe, a four-dimensional fabric called space-time. Massive objects like stars and planets create dips in this fabric, and other objects simply follow these curves, which we perceive as orbits. A black hole is what happens when this curvature is taken to its absolute extreme. If you compress enough mass into a small enough volume, the curvature of space-time becomes so intense that it effectively tears a hole in the fabric. This creates a region from which nothing, not even light, can escape. The boundary of this region is called the event horizon. It is not a physical surface. It is a point of no return. Once you cross the event horizon, all possible paths in space-time lead to one place, the center. According to general relativity, at the center of a black hole lies a singularity, a point of infinite density and zero volume, where our current laws of physics completely break down. This is the ultimate unknown in modern science. The birth of a supermassive black hole, as may be happening in the infinity galaxy, is therefore not just the creation of a massive object. It is the creation of a new event horizon, a new boundary to the known universe. It is the birth of a new singularity, a new tear in the fabric of reality. The direct collapse of a gas cloud containing millions of solar masses is a process that is happening at the very edge of our physical understanding. The immense gravitational forces involved would warp and twist space-time in unimaginable ways. The final moment of collapse, when the event horizon flickers into existence, will be a truly spectacular event, hidden forever from our view within its cocoon of gas, but fundamentally changing the structure of space-time in its local neighborhood. This connection to fundamental physics is what elevates the discovery from a fascinating astronomical finding to one of deep and profound significance. We're not just observing a new way to make a big object. We are observing a process that directly engages with the most extreme predictions of our best theory of gravity. It is a real-world laboratory for studying physics under conditions that we can never hope to replicate on Earth. As we continue to study this object, we're not just learning about galaxies. We're probing the very nature of space-time, gravity, and the ultimate limits of physical law. It begs the question, are our laws of physics truly universal, or do they begin to fray and change in the presence of such incomprehensible extremes? We have learned about the infinity galaxy by observing its light, its infrared, X-ray, and radio emissions. But there's another way to perceive the universe, a way that was opened up to us only in the last decade. This is the ability to detect gravitational waves, the ripples in space-time itself that are created by the most violent cosmic events. In 2015, the LIGO Observatory made the first ever direct detection of gravitational waves from the merger of two stellar mass black holes. This discovery opened a new window on the universe, allowing us to listen to the cosmos in a way that was previously impossible. The merger of two supermassive black holes, like the ones that will eventually merge in the heart of Mokomata, would be one of the most powerful gravitational wave events in the entire universe. The problem is that these mergers are so massive that they produce very low-frequency gravitational waves, waves with wavelengths of millions of kilometers. These waves are too long to be detected by ground-based observatories like LIGO. To hear them, we will need to build a gravitational wave observatory in space. This is the goal of the Laser Interferometer Space Antenna, or LISA, a mission currently being developed by the European Space Agency and NASA. LISA will consist of 3 spacecraft, flying in a triangular formation millions of kilometers apart, connected by laser beams. By measuring the tiny changes in the distance between the spacecraft as a gravitational wave passes by, LISA will be able to detect the mergers of supermassive black holes anywhere in the universe. Now, how does this relate to the infinity galaxy? The direct collapse of a massive gas cloud to form a new supermassive black hole would also be an incredibly violent event. While the collapse itself might be relatively symmetrical and not produce strong gravitational waves, the newborn black hole would be a new and powerful gravitational player in the system. As it interacts with the 2 original supermassive black holes from the parent galaxies, it would create a complex, chaotic 3-body dance. This dance, and the eventual mergers that would result, would produce a symphony of gravitational waves that a future observatory like LISA could potentially detect. The signal would be unique, telling us the story of a system with 3 supermassive black holes. This is a tantalizing prospect for the future. We may one day be able to not just see the light from systems like the infinity galaxy, but to hear the sound of their space-time ringing as their black holes dance and merge. This would give us a completely independent way to verify the direct collapse model and to measure the properties of the newborn black hole with incredible precision. It is a reminder that our exploration of the universe is constantly evolving. with new senses and new tools always on the horizon. It makes us wonder what other cosmic phenomena are currently invisible and silent to us, waiting for a new kind of observatory to be invented that will finally allow us to perceive them. In our journey through the cosmos, it is easy to be overwhelmed by the immense scales of space and time, by the exotic physics of black holes and galaxies. But it is crucial to remember that at the heart of every discovery is a profoundly human story. The discovery of the infinity galaxy is not just the result of a single telescope or a single brilliant idea. It is the culmination of decades of work by thousands of people from all over the world. It is a story of vision, dedication, and collaboration. Think of the telescopes themselves. The James Webb Space Telescope was a project that took over 20 years to design, build, and launch, involving the work of thousands of engineers, technicians, and scientists from multiple space agencies. The Keck Observatory, the VLA, the Chandra X-ray Observatory, each of these represents a monumental effort of human ingenuity and a long-term commitment to fundamental research. These are the tools that we, as a species, have collectively built to extend our senses beyond the confines of our small planet. Then there is the scientific collaboration. The team led by Peter Van Dockum is an international one, with researchers from different institutions in different countries, each bringing their own expertise to the table. Some are experts in analyzing JWST images, others in interpreting Keck spectra, and others in running complex computer simulations to model the physics of the merger. Science at this level is a team sport. It relies on the open sharing of data, the critical peer review of ideas, and the collective effort to assemble a complex puzzle from many disparate pieces. The data itself, from a survey like Cosmos Web, is made available to the entire astronomical community, allowing anyone with a clever idea to explore this new territory and make their own discoveries. This human element is perhaps the most hopeful part of the story. In a world so often divided, the pursuit of scientific knowledge is one of the few endeavors that truly unites us. The light from the infinity galaxy traveled for billions of years to reach us. It was captured by a telescope built by an international consortium. The data was analyzed by a team of scientists from around the globe, and the results were published and shared with all of humanity. It is a testament to what we can achieve when we work together, driven not by profit or by politics, but by a shared, fundamental curiosity about the universe and our place within it. It reminds us that our greatest strength as a species may be this ability to pool our intellect and our resources to ask and answer the biggest questions of all. We have discussed the birth of a supermassive black hole, but what is its ultimate fate? And what happens to all the things that fall into it? This brings us to one of the deepest and most perplexing puzzles in theoretical physics, the black hole information paradox. In physics, information has a very specific meaning. It is the complete description of the physical state of a system. A fundamental principle of quantum mechanics is that information can never be truly destroyed. It can be scrambled, rearranged, or hidden, but the total amount of information in the universe must be conserved. Black holes seem to violate this principle. When a star, a gas cloud, or an astronaut falls into a black hole, all the information about their intricate structure seems to be lost forever, crushed out of existence at the singularity. All that remains is the black hole's mass, spin, and charge. This created a profound conflict between general relativity and quantum mechanics. Then, in the 1970s, Stephen Hawking made a stunning theoretical discovery. By applying the principles of quantum mechanics to the edge of a black hole's event horizon, he showed that black holes are not completely black. They should slowly emit a faint thermal glow, now known as Hawking radiation. This radiation causes the black hole to slowly lose mass and, over an unimaginably long period of time, completely evaporate and disappear. This led to the paradox. If the black hole evaporates, what happens to the information of everything that fell inside? The radiation that comes out seems to be random and thermal, containing no information about what made the black hole. Does the information get destroyed after all, breaking the laws of quantum mechanics? does it somehow escape, encoded in the subtle properties of the Hawking radiation? This is a question that physicists are still grappling with today, and its solution will likely require a new theory of quantum gravity that unifies Einstein's relativity with quantum mechanics. The newborn black hole in the infinity galaxy, then, is not just a gravitational monster. It is a vault of information, a cosmic puzzle box. As it consumes the gas from its parent cloud, it is swallowing the information about that gas. And over the next trillions upon trillions of years, long after all the stars in the universe have burned out, it will slowly radiate that mass energy back into the cold, dark universe. Understanding the fate of that information is one of the key quests of modern physics. The birth of this new black hole is not just the beginning of its life as a cosmic object. It is the beginning of a new chapter in one of science's deepest and most enduring mysteries. Let's take a brief detour into a more speculative, but increasingly debated philosophical idea, the simulation hypothesis. This is the proposition that our entire reality, from the smallest quantum particle to the largest galactic supercluster, is in fact an artificial simulation created by a far more advanced intelligence. While it sounds like science fiction, some physicists and philosophers take it seriously as a logical possibility. The argument often goes that any civilization that survives long enough to develop sufficient computing power will likely run ancestor simulations to study their own past, and that the number of simulated realities would eventually far outnumber the single base reality, making it statistically more likely that we are in one of the simulations. Most of the time, this hypothesis is untestable. How could we ever prove or disprove that our reality is a simulation from within the simulation itself? However, some have suggested that there might be clues. A programmer might cut corners or use simplified physics to save on computing power. We might find that the laws of physics are not perfectly smooth, but are built upon a discrete, pixelated grid at the smallest scales. Or perhaps more poetically, the creators of the simulation might leave an artistic signature, an Easter egg, something so strange or symbolic that it hints at an intelligent design. And this brings us, in a speculative way, back to the infinity galaxy. Here we have an object of profound scientific importance, a potential key to understanding the formation of supermassive black holes and the evolution of the universe. And it just so happens to be shaped exactly like the mathematical symbol for infinity, a concept deeply tied to abstract intelligence. The symmetry is almost too perfect, the symbolism too potent. Is it possible that this is a hint? A small, beautiful piece of cosmic art left in the code of our universe by its creators? Of course, this is pure speculation. The shape can be perfectly well explained by the laws of gravity and the specific dynamics of this particular collision. There is no scientific reason to invoke a cosmic programmer, but the thought exercise itself is valuable. It forces us to confront the limits of our own knowledge and the nature of reality. It makes us ask, what is the difference between a universe that follows a set of elegant mathematical laws and a universe that is a computer program running on an elegant mathematical code? Does the distinction even matter? The infinity galaxy, in its perfect form, serves as a Rorschach test for our cosmic beliefs. You can see it as a beautiful but random consequence of impersonal physical laws. Or you can see it as a wink from the universe, a hint of something deeper and more mysterious. Either way, its existence enriches our experience of the cosmos and deepens our sense of wonder. We have traveled across billions of light years and billions of years of cosmic history. We have journeyed from the established science of galactic collisions to the speculative frontiers of quantum gravity and simulated realities. And it all began with a single, strange shape in a new image of the sky. What then is the ultimate legacy of the discovery of the infinity galaxy? First and foremost, its legacy is scientific. It has provided the first compelling, direct evidence for a new and powerful mechanism for the formation of supermassive black holes. The direct collapse model is no longer just a theory on a blackboard. It is a theory with a candidate object that can be studied and tested. This discovery has the potential to solve a long-standing puzzle of the first quasars and to fundamentally rewrite our understanding of the coevolution of galaxies and their central black holes. It has opened a new field of research, the search for and study of newborn supermassive black holes. This single object will be a touchstone for research for decades to come, a target for every new telescope we build. Its legacy is also technological. It is a stunning validation of the power of our new generation of observatories, particularly the James Webb Space Telescope. It demonstrates how a revolutionary new instrument can immediately begin to answer old questions and, more importantly, to raise new ones we didn't even know to ask. It is a showcase for the power of multi-wavelength astronomy, proving that a complete understanding of the universe requires us to look in every kind of light. Finally, its legacy is philosophical. It has given us a new icon of cosmic creation. The image of the infinity galaxy is one that will likely become as famous as the pillars of creation or the Hubble Ultra Deep Field. It is an image of profound beauty and profound meaning. It represents the universe's capacity for surprise, its ability to produce structures of elegant symmetry and deep significance. It is a story of creation from chaos, of a new beginning forged in the heart of a violent collision. It reminds us that the universe is not a static, finished thing, but a dynamic, evolving place where new and wonderful things are being born even now. It is a symbol of endless possibility. The legacy of the infinity galaxy is that it has made our universe feel a little larger, a little stranger, and a little more infinite. Our exploration of the infinite is drawing to a close. We have journeyed to the edge of creation, witnessed the potential birth of a cosmic monster, and contemplated the deepest questions about our reality. And now we return. We leave the distant universe of colliding galaxies and newborn black holes, and we travel back to our quiet, stable corner of the cosmos. We return to our solar system, to our home. Here, under the familiar light of our own star, the universe feels a little different than it did before. The discovery of the infinity galaxy has added a new layer to our cosmic perspective. It reminds us that the peace and stability we enjoy are not the norm. The universe is a place of constant change, of violent collisions, and of sudden, spectacular creation. Our own galaxy's quiet state is temporary, a brief pause between a chaotic past and a dramatic future. This knowledge does not diminish the beauty of our home. It enhances it. It makes our stable sun, our blue oceans, and our living world feel all the more precious, a rare and beautiful island of calm in a turbulent cosmic sea. Remember the planet you thought of at the very beginning of our journey? Your favorite world. Now, as you look up at the night sky, you can add a new object to your mental map of the cosmos. Not a planet, not a star, but a symbol. An infinity sign written in starlight. A place where a new chapter of the universe's story is being written. It is a reminder that there's always more to discover, that the universe is filled with wonders that are waiting just beyond the edge of our vision. Thank you for joining me on this plunge into science. I hope this journey has brought you not just knowledge, but a sense of peace and a deeper connection to the magnificent universe we are all a part of. As you close your eyes and drift off to sleep, may your dreams be filled with the quiet, endless dance of the galaxies. Rest well.